Gotta freaking love technology. All right. We're live. Make sure everything's coming through. You got it on your end? Nice. Okay. Yeah. Yeah, it's about right. Something like that. All right. Ain't technology fun? I just don't get it. Things should just work. Why don't they work? Why does it have to always fight? And not everything has to be a fight. But yet again, it does. Anyway, all right, so getting into air-cooled chillers. Last night we went over a lot of the mechanical principles. Tonight I actually plan on going into the controls and operations side and just how we stage, why we stage. So to kind of give you a quick rundown, we'll get into just some basic parameters. We'll get into some startup sequences. From there, we'll talk about some components and safeties, and we'll be finishing things up with how we do our loading control, which I think is probably the part that is the biggest mystery, is why the logic chooses how to load and how to make the adjustments to the system, because a lot of things goes into as we're staging the compressors and staging in terms of chillers, especially with a screw machine. Why do we see? This is what I'm talking about. This is what I'm talking about. Audio. I'm not muted. Let's figure this out. Yeah. Okay. Did you forget to turn the volume up? Sorry. You got me freaked out. I'm already having freaking issues over here. Now we got guys. I'm gullible right now. You got to be careful. All right. So yes, when you start talking about screw machine staging, it's a whole nother ball game. So we'll get into that. So some basic parameters, things we've got to look at is when a machine wants to turn on, or it's a standing operation, we've got two ways of doing it. Most any chiller that's been produced in the last 20 years has some kind of onboard scheduling system to where it has the capacity to control itself to some degree. You can go in, program a schedule, program off times, on times. Not every machine, but a lot of them. Vast majority of the applications we have, though, that almost never gets used. It's typically automation comes in, has some kind of start-stop sequence involved. So that's ultimately one of the first things that in our applications a chiller is going to be looking for, is it needs a start signal before it'll do anything. Now, a critical piece to any kind of chiller is water flow. So then the next question becomes, how does that water flow get established? Is the chiller controlling that pump, or is the automation controlling the pump? And it could be either. Just depends on the building, depends on how it's designed. And we've even got some buildings that, it's a much older concept that you won't see it on anything new, but the start-stop on some chillers may be the flow switch. So on very old designs, that was a way that they did it, especially back in pneumatics, was the automation system would engage the pump for the plant or for that chiller. And then when the flow switch on that chiller closed, that triggered the start-stop for the machine to turn on, which I don't like that at all. That setup creates problems, and honestly, a lot of modern chillers won't allow you to do that. So, for example, one of the plants we have where we took an RTAA out, put a CGAM in, that CGAM and its the delays that it has in place, it's too smart for that. And we started having all kinds of flow alarms because we were losing flow before we shut down, which is a problem with that design. Is if the start-stop is the flow switch, well, that means to stop the chiller, we have to stop flow while it's still running. It's horrible, absolutely horrible, but that's the way it was done for a period of time. So you may still run into stuff like that out there. You have to be really careful of that. Anyway, that particular one, we had to go in and update it. And what we did was they didn't want to upgrade the building controls. So we took the start-stop signal for the pump, routed it to start-stop the chiller, and then gave the chiller control of the pump. And that was our solution. Instead of spending a ridiculous amount of money trying to run control wiring, 1,000 yards underground across a parking lot, it just rerouted there inside the plant.
They're a pretty big parking lot.
Yeah, no, it's, yeah. Well, by the time you get through the parking lot and then into the building, into the control panel and run, and it's a lot of freaking wire would have been required to do that. It just didn't make any sense, ultimately. And the chiller, a lot of your modern chillers much prefer to control everything themselves. They don't have to, but they like to. And that's one of the trends that I've seen over time, and it's something that the manufacturers I see are doing. There's a lot of new equipment out there that the control panel on this stuff is its own internal automation. It has its own capacity to run an entire plant. Daikin, for example, their setup on their water-cooled side can run its own cooling tower, can do its own variable speed fan, can control its own pumps. Like it's a literal control system built into a chiller. Huh?
I had a CGAM that did that.
Yeah, that's what they have. And it doesn't require the building automation. We don't have any buildings that actually utilize that. But you rewind, 20, 30 years ago, and the chillers didn't have all those same capacities, at least not the way they do today. So you needed that additional support system for the controls in order to operate that machine. So where all this is coming from is you need to start-stop from somewhere. And then beyond that, you need a ability to have flow, whether the automation tells flow or the chiller brings that pump on itself, either or. So a lot of the times, if we have a common header loop, which air-cooled, we really don't see that much. Most of the time, that's more centrifugal water side. But in the event that you had something like that, you would have to have ISO valves. And I have had a system like that where it was one central chill water pump, and it had two air-cooleds. I think they were they weren't CGAMs. They were RTACs. There we go. They were RTACs. And the building automation would either open this ISO or open that ISO, depending on which chiller they wanted to run. But they were a lead lag setup. So that's just another way of doing it. And what'll happen is if the chiller sees flow when there's no call, then it can register that as a bad flow sensor. And if it loses flow before it gets a shutdown command, or it loses start-stop, then it's going to register that as a flow loss problem, and it's going to lock itself out. So those are things you have to be careful with, especially on newer machines. So we've established the start-stop. We've established flow. The next big parameter goes into, you can give a chiller a start-stop signal, and you can give a chiller flow, but it doesn't mean the chiller is going to turn on. Why? There's one more parameter that has to be met.
Set point?
What's our deviation from set point? So we have to, and that's going to be dependent upon the chiller, right? So it could be 2 degrees, 4 degrees, 10 degrees. So if our set point's 44, and for whatever reason we're pushing 46 degrees and we have a 4-degree dead band, then that chiller is probably not going to turn on. It doesn't need to as far as it's concerned. It got everything else. So you have to have the load component, as in our temperature, our leaving water has to be high enough. And don't get hung up on the entering water. Most systems don't pay that much attention to the entering water unless it sees them invert, which is its own safety. So, we can dive into more of the safety sides later. So yes, start, flow, and set point. Now, going into startup sequence, one of the first things that a chiller is going to do is it's going to start looking at the safety circuits. Are any of the high pressures tripped? Are any of the, do we have flow? Are we running too cold of water? Is our, we wouldn't have that there. I'm trying to think what would be some pre-startup safeties. Obviously, no low pressure.
Coolant circuits, if it has those inhibitor bumps and all that.
Well, so for the inhibitors, there's not a safety monitoring that unless, so if in that case, you're talking a York design. If the VSD plate sensors were bad, then, they say they're reading too high of a temperature, for example. That could trigger something, but that wouldn't be a verification of the inhibitor flowing. So there's nothing truly monitoring the inhibitor system at that point, which we didn't even get to that last night. So that goes back into that other thought. We got to keep going. Anyway. Enough squirrels. So yes, safeties have to be closed. So once it verifies safeties are closed, we've met startup parameters, it's going to go into a recirculation time. And if the machine, a lot of times that can be just a regular 3 to 5 minute timer most of the time. It's going to sit there. It wants to circulate water, let the loop stabilize, let everything do what it's supposed to do before it brings on any mechanical cooling. That helps it verify that the chill water temperature is actually needing chill water. If there's any kind of irregularities in the loop, it gives it a few minutes to stabilize that. So there's a lot of benefits to doing that. And there's a lot of control systems where you may not even get the start-stop from the automation until after the automation does that recirculate time for you. But then the chiller also has its own recirculate that it's going to pay attention to. So you have to keep that in mind. You may have 2 delays stacked on top of each other. So those are just little variables you have to think through. But typically, when you're in that condition, most of them will give you like a waiting to start on the display. So Train, York, you'll have something pop up of, you'll have some kind of run inhibit or, waiting to start, or anytime you see something like that, you're just waiting on delays. Whether that be flow, whatever delay it's looking at that time. Most of the time it's a flow delay. So we've got our start stop, we've got our flow, we have our load, we're ready to turn on, our safeties are good. So we get past the safeties, we've satisfied our minimum flow requirements. Now we've got to decide which circuit turns on. Because most of the time we're dealing with multiple circuits, at least 2, if not up to 3 or 4. So most systems are set to do circuit load balancing based off of, usually I like to do mine off of starts. Some machines I think will base it off of run hours, or run hours will factor into the equation. But my personal preference is basing it on starts. I like to do a balanced start. One drawback to that is sometimes the hours could look different. And so you may have one that just got to run longer. And if you have a machine that's having issues with a circuit tripping on safeties, it may have a whole bunch of starts and very little runtime. So I don't know that there's one perfect way of doing that. Just my preference is on start. So if circuit 1 has 100 starts and circuit 2 has 99, I would expect circuit 2 to engage as my lead.
Do you do it that way because starts is typically the hardest on the compressor and you want to minimize that, or?
Typically, yeah. Yeah. Right. And you also get into a world where that's less of an issue with variable speed or soft starting systems, right? So we don't have that hard punch at the startup. So that, then you get into a situation where does it make more sense to balance based off of hours, because we're not having this huge inrush. So we're not putting that extra stress on it. So like I said, in my opinion, I don't think there's a perfect way to look at it. It's the machine you're working on and your personal preference. Mine starts. And some of you don't even give you the option to base it. You either do a dedicated lead lag where one circuit is your dedicated lead circuit. So that is one option. Or you do a balanced load where it cycles between the two based off of starts or hours or whatever it is. You could also have a system to where if it's tied into BACnet or Modbus or the communication system, that could be coming from the automation. And they can write to a point in the chiller to where the automation decides who gets to cycle as our lead. And they could base that off of days. They do the same thing with chillers. So say you have redundancy. So you got 2 chillers on site. We're going to turn chiller 1 on for this week and chiller 2 on this week. And they cycle the chillers. Well, they can actually do the same thing in the circuits as well. If they BACnet into the system and communicate directly with it, they can write 2 different points to tell it which circuit they want lead for that week.
Yeah, I know a building that does that.
Yeah, I mean, it's
Yeah.
So that becomes the next parameter that the system is looking at. And keep in mind, we've gone through all these parameters. We haven't turned on yet. We have yet to actually see a compressor kick over. So once we decide who gets to turn on, the next stage of that sequence is going to be EXV calibrations. And vast majority of the systems we have today have EXVs. And TXVs do still exist, but they're pretty rare. And anything in the last 20 years, most of them have some form of an EXV on them. So yes, we're going to do an EXV calibration. With that, as a means of minimizing load, an EXV is going to start closed and then open as the machine runs, the circuit stabilizes, and everything begins to balance out. So what it will do is when the machine is off, that valve should be closed. And you'll hear it, it'll start to tick, it'll run to a full open state, and then it's going to run fully closed. It knows that that valve is calibrated at that point and ready to turn on.
If you're lucky, you can see it in the sunglasses.
Right.
If you're lucky.
Now, one caveat to that is all of this is at like an initial startup for the first time usually after a power cycle, or after the machine has been cycled to an off position. If it's just doing a normal everyday staging and cycling, that EXV step may not come into the equation. And that's how you get valves out of calibration.
The C-cams, I know you can do it on the C-cam because the ones that I used to take care of, it would calibrate the EXV because this was a process place, so it normally, they stayed running all day.
Right.
It would do it every 24 hours on it, for the, what is that, the 800, the UC 800 or whatever it is.
We have the 800 or the 530.
It's
The Dynaview.
I don't know why I said 800. It was the CH 530.
Yeah.
And it would do it every 24 hours for both circuits.
Mm-hmm.
It would open, close. You could hear it right at the beginning of the 6 o'clock in the morning. It was
right. So that one is not an automatic, and I want to point that out. That's just one of the things that it will do. And like you said, a lot of the newer machines are building in some of those capacities where it will do a timed calibration because it is an issue. EXVs on these machines don't have a feedback. The machine doesn't actually know the real position. Whatever that display is telling you is calculated, and it's based off of a time. It's a floating point valve. So just like we talk about floating point actuators, the EXVs function on the same principles. They're just a timed valve, and that chiller knows that it takes 90 seconds to full open or full close. And based off of how many pulses it gives, it knows that it should be at 500 steps at X position based off of that. But if that EXV begins to, the threads on it begin to have wear, or the stem begins to stick and has any kind of resistance, it can start to skip steps because it hangs up. And so every single time that happens, even if there's just one control point where it gets a little stiff, every time it catches that point and it skips a step, it is that much further out of calibration. And after an entire day of cycling past that point, you've now got a valve that the machine has no idea what position it's in until it does a calibration. Yorks are probably the worst I've seen on the air-cooled side with struggling with getting out of calibration. Trains will do it too, but I just haven't seen the same consistency out of the train machines as I have the Yorks. Way more issues with their EXVs. Yeah. Okay. Now we've actually done our calibration. At that point, we're actually to the point of turning everything on. We hit the go button, whether it be Y delta start, whether it be variable speed, or just an XL contact. So XL being it just hammers like a regular contactor and goes. So just checking some of the comments here. Everybody's just chatting. Okay. Every machine is always going to start up fully unloaded. Or if it's, say, a screw or a recip, you're going to start with just one compressor. And typically, if that compressor has unloading capabilities, Well, no, it shouldn't go straight to unloading at startup. And when it's bringing that circuit in, it should allow that compressor to come in, stabilize, and it's not going to start unloading that compressor until later. But either way, a screw, remember we have a slide valve to control how much volume that screw bolts are able to push. That is going to start in the fully unload position, meaning we're moving the minimum amount of refrigerant possible. And that keeps our inrush current down. And that's another reason why we want to start with the EXV closed, is so that we can pull that evaporator down without putting additional load on the compressor, because at that point we can start feeding it. And a very common thing you'll see at startup is your evap saturations will dip. So a lot of machines will ignore the low pressure for 30 seconds at startup, so that EXV has a chance to open after that compressor is rolling and start to feed that evaporator to get that pressure and everything back up before it just nuisance trips. A lot of modern machines will use both transducers and low pressure switches, regular contact switches, or they may not have switches at all. We're seeing a trend where as control systems become more in-depth, become more reliable, they're not even putting switches in there anymore. High pressure, low pressure, you won't find them. It won't be a wired switch. It'll strictly be logic inside the controller reading a transducer. Problem with that transducer goes bad, now your safety is skewed. So that's one of my gripes as to them doing that. Just trying to make sure I didn't miss anything. Okay. So at this point, we're rolling, we're moving refrigerant, metering valves are opening. As they open, the final parameter before everything just goes into a normal run is pull down. So we talked about that a little bit yesterday, but essentially a pull down is anytime the machine comes in with an elevated load, it's going to go into a pull down state until it is able to get that temperature down to set point. Now, what makes a pull down is the way that it stages the circuit will be different. So we have a thing called a current limit. Current limit is actually how we stage a compressor. And how deep do I go now versus later? We'll hit it now. Honing in on a screw machine, not talking about scrolls, right? So a scroll is pretty straightforward. We don't have, you have compressors that turn on and off. So if a scroll went into a pull down, in order to prevent overloading the condenser and having high head pressure issues, it's going to limit the number of compressors it can bring in order to control head pressure readings to pull, say, a 70-degree entering water down to 45. At the same time, if we've got a machine that's designed for a 10-degree split, we want to stay within that parameter. So if we just throw everything on at once and create a 20-degree split, well, it's not good for the machine. You're putting a lot of excess load, and those condenser coils are not going to be able to keep up. Because that's something you can do. You can stage that thing up so much, the coils can't support the load because you're moving so many BTUs, and you're going to start tripping these random high head pressures, and it's because you don't have a pull down set properly. With a screw, though, that load percentage is based off of RLA, not valve position. When I mean valve, I mean slide valve. And this is a shift in how you think about things. when that compressor says it's at 100% loaded, that does not mean that that slide valve is pushed to 100% position, to where that entire bolt assembly is moving refrigerant. What that means is that you've put enough volume of load and you've got a high enough compression ratio across that chiller, or I'm sorry, that compressor, to drive your motor amps to 100% of RLA. And if you were to actually slide that slide valve, all the way to the full position, you would see your RLA spike out of control. I mean, it could go as high as it needed to. You can push that to the point where the motor doesn't have the torque to turn it anymore. So think about that as we kind of go through it, and we'll get more into the loading and why it loads the way it does later. But for a pull down current limit, most of the time you'll see those set to a 60 to 80%. I don't have a preference one way or the other. I think it completely depends on your application and the equipment that you have. If you've got a system that yeah, I'm not even going to put a parameter on it.
From set point, would you want to start maybe a little lower?
Well, most of your pull downs, you don't have, like, there's not a step 1, step 2 on a pull down. Once you enter a pull down state, whatever that pull down set point is on the current limit, that's what you're going to run.
Which is why you see on drives. Right?
See what?
That's why you'll see systems like you're talking about on drives.
Well,
it's limiting the speed, it's limiting the
well, yes. So a variable speed compressor doesn't have a slide valve.
No.
So instead of controlling via slide, we're controlling via speed. And 100% RLA doesn't mean full speed. Doesn't mean 60 hertz or 200 hertz, you know, if you're York. So in the same way that it won't let that slide move all the way to the load position, like 100%, like won't let that slide. Well, that's so. The reason I'm pausing is you have to be careful here. There's two ways of looking at fully loaded. There's fully loaded on the motor or fully loaded on the screws. And that chiller control system cares a lot more about full load on the motor. And that's what it's really paying attention to. So you have to be careful. It's a different way of thinking about it. We're putting a full load on the motor. So when we set these current limits, it's a current limit. It's a limit on the motor. It doesn't mean that those screws are moving the maximum amount of refrigerant that they can. It means that motor is pushing as hard as it can under the given conditions. And as the load and the compression ratios reduce, your amps will drop because there's just not, the load's just not there. And that changes things. So then you can apply more load on the motor, or not even the motor, I'm sorry, you can apply more load on the screws, which will then increase the load on the motor to push more refrigerant.
Okay, I understand. It's kind of they stay similar, but it's still like it's a floating. It's kind of it's a floating point. This is 100% RLA, but it's not 100% of what it can do. But it's
Yes.
for the given parameters. This is where you're sitting. This is where you're sitting, and they kind of they move up in like linear. I don't know how to say the word right now, but in a linear fashion.
Yes. No, yes.
That makes sense.
So I got a question. Can I draw a graph of the load over time?
On pull down?
I can try.
Overtime.
I can try. Let's see. That's a good test, honestly. So let's say,
Love that straight line.
what would our parameter be? So we'd have, we're moving, this would be our, we'll make this
Time on the
Motor
bottom.
RLA time.
Well, he said over time, right?
Well,
Your
so
time would be on the bottom and your RLA would be the other one, right?
if we have RLA and actual load, so this would be a slide position. Now there's one other parameter in this, and this is compression ratio, but that kind of plays into the slide position. But so let's say we had a 70-degree entering, and our set point is 45. We've got a machine that's designed for a 10-degree evap split. Yeah. Okay, so these are our basic design parameters. We just turned on. We've now got to make this 70 degrees, pull it down to 45. We can handle a 10-degree split per design on that evaporator, which means that we can pull this immediately down to about 60. So what we would end up doing is our slide position would be down here, but RLA, how am I going to draw this? I got to figure this out. RLA would be over here. So
Why not put a min and a max on your RLA side? Wouldn't that make it a little easier?
so this would be slide position 100%, 0, RLA 0, RLA 100. Let's say we had a 80% current limit. So as we pull down, as we pull the water down, I'm trying to picture this in my mind. Our RLA, we would remain constant. It'd kind of be a straight line. I guess we would remain constant, but our slide valve would increase as the water temperatures decrease. But our RLA remains constant. Actually, so I think I should put my water down here. I think I can make that make sense in my brain. So we know that, so let's say our current limit is 80%. So on this graph, the current limit doesn't change. We maintain 80% RLA across. But our water leaving down here, let's say we're at, we're going to go backwards in my brain. So we're going to make this 70. We're going to make this 45. We would come up, say probably, I think the minimum would be probably like 20% slide. And as our water temperature drops and we get to 45, you're going to see your slide position increase. But we maintain an 80% RLA the entire time. So the motor load maintains the same, but the slide in the compressor, or the speed of the compressor, depending on what style you're working on, is slowly increasing as our water decreases. Does it?
Yeah, because if you
You could
have
draw a backwards line for your RLA, right?
well,
When you go the other
evaporator is adding all that pressure because it's higher, you're adding pressure. So if you had a 100% slide position, you would actually start pushing back because you wouldn't actually be able to create that differential pressure, right? Because you'll start freeze thinning and pushing back. If you open it all up, there'd be too much pressure on the condenser. And just, right? No, am I thinking about that?
Well, no. So you're thinking centrifugal. You're thinking a surge on a centrifugal, which this is. You would end up putting so much compression force against the motor that it wouldn't have the torque to push it, and so you would end up tripping the motor on a current.
But it's the same concept, though, right?
No, it's not the same concept.
Okay.
They're different things
My
entirely.
head is making sense, but I guess I'm not explaining how I'm thinking it properly. Continue.
Yeah.
I'll figure that out later.
So wouldn't head pressure increase and RLA, wouldn't head pressure and RLA increase? So the head pressure, keep in mind your head pressure is relative to load. Okay? And I've done several classes in the past talking about, subcooling and head pressure is completely relative to the load that you have on the evaporator. So the more heat we're inputting into the system, the more it has to reject. But ultimately, if we limit that RLA, theoretically, we end up having more head pressure on this end of the spectrum with a really high load on the evaporator, and that head pressure becomes easier to manage as our load on the evaporator reduces. Right. Well, yeah, the whole system load is decreasing. It's not so much that the saturation is decreasing, but the actual input BTUs on the evaporator are dropping. And as the input BTU is dropping, our output can come down a little bit too. And then once we get to the point where we no longer need, to limit anything, and so we're no longer having an issue with a 10-degree split, and so we hit our 45 set point. Now we can start backing off on the staging, and we so say we get down to 53. Well, 53, which would be an 8-degree split across that evap, now that condenser has a much easier time keeping up with the load.
Would that be when you would release it back to 100%?
So yes. So at that point, once we have, there's two ways that I've seen current limits work. Either time or based off of deviation from set point. So once we get close enough to set point that we're no longer in an excessive load, then we allow that system to go back to 100% current limit or whatever that current limit was. In some systems, you may have a pull down of 60% and they don't want to see more than 80% on the compressors. Fine, right? It'll go back to that 80 or whatever the set parameter is on that limit.
Still your max.
Right, it's the max. So whatever that max is would be that RLA. And a lot of your air-cooleds will run 110, 115% on the RLA limits, normal. Now, my personal preference, I choose to limit them at about 100% and don't push that load envelope the same. But from the factory, I mean, they'll come in 110% RLA on the current limit straight out of the box. Well, you're talking about they push that circuit. I can't fully explain all their logic as to why they choose to do that, but they are willing to push that compressor a little beyond the rated RLA.
Would that be because?
Yeah.
Would that be because it's not supposed to be doing that all the time, so they're kind of willing to go past that threshold for just a little bit until they get down to what it was actually designed for?
genuinely, I'm not 100% sure, because in a real case scenario, it can push that and run at 105, 110% RLA for an extended period of time. Especially if it's, because so this gets into staging and the whole loading, and I'm getting a little bit ahead of myself. The chiller decides, I need more than this circuit can provide me, based on I've maximized this circuit's capacity and I can no longer achieve set point. I need to bring in the other circuit in order to do so. And an automation system uses similar logic, where this chiller is enabled. I'm running it at maximum capacity. A lot of times they'll have like a 30-minute, right? We got a couple of guys. Yeah, they'll have like a 30-minute delay, to where if that chiller cannot process that loop down to set point within a 30-minute time frame, they will enable the lag chiller and let them both run together to process that load down.
All the way to set point.
Yeah, to set point, and once it gets down, and once it holds set point or lower for 30 minutes, and the chillers can start to stage down, then it will drop that lag back out and just run the primary or the lead. In the same way, the chiller is using the exact same logic to control the individual circuits. It's going to max this one out until it sees that this one can't stabilize it. So that there's a scenario where you could run over 100% RLA for an extended period of time before the chiller decides, okay, I need to bring in somebody else.
That's a lot like cascading on a boiler.
Mm-hmm.
When you have multiple boilers, they'll cascade themselves like that.
Yep.
Then they'll back themselves down.
Mm-hmm. Exactly. So this is current limiting. Once we hit that pull down, we're going to limit that so that it can't overstage itself. Because what will happen when you have really high load conditions, the load and pull down are very unstable conditions. And what you don't want to do is you don't want to push your head pressure too high. You don't want to add more stress and waste energy, because that's one of the things is if you allow that system to completely stage at maximum at pull down, you're burning a lot of electricity at that time. But also you can push that system to run on the edge of its safety limits. And when you're in a pull down state and you're outside of normal design parameters, the system is very unstable. The refrigerant pressures are unstable, the loading is unstable, the water temperatures are unstable, and there's a lot of fluctuations happening. And what that'll lead to is you'll nuisance trip trying to pull down, whether it be high pressure, low pressure, current limit, whatever it is, you'll start to have nuisance trips on circuits before they ever get the loop fully pulled down. And I had this exact scenario on a centrifugal recently. It didn't have a current limit programmed. It was defaulted to 100%. And during a heavy pull down, it had enough fluctuation that all it takes is to trigger that safety. That's all it's looking for. You tap it, it's going to shut down to protect that system. And that's what it would do. It would tap that safety and shut it down before it ever got to process the loop down.
Yeah, slow and steady wins the race.
Yes, absolutely. Slow and steady.
Is that the one I was doing PMs on? Is that one?
Well, you've done a lot of PMs
Yeah,
on,
sure.
so
In
that
the
doesn't.
last month or so.
Yeah, that one.
Like the last month or so. That narrows it down.
You've done quite a few PMs in the last month or so.
You
No, not on that one. Anyway,
This memory's on fire.
CR valve used on chillers and CPR valve. CPR. Pressure regulator is what you'll have to give me that acronym, please. I'm drawing a blank on CPR. We may call that something different here. Anyway. Okay, pull down. Once we've satisfied the pull down parameters, we just go back into normal operation. And until something crazy happens, it's just going to run.
And it'll release that current limiting at that point?
Yes. Yep. Yeah, it'll come out of the current limit set point for pull down and default to whatever the actual current limit is on the machine.
And that's based on your split?
What is?
Your water, your inlet and outlet water?
It could be, more specifically, not inlet outlet. It would be deviation from set point.
Gotcha. Well, yeah.
Or time. So if the machine was completely off and it goes into a startup, it can either go into a pull down regardless of deviation or deviation itself.
Gotcha.
You're doing load temp, aren't you? Like rack systems. Yeah, no, we don't use that. At least not that I've seen. You can correct me if I'm wrong, but that's something you're going to find on a rack system doing like supermarket work. We'll come back to that. Okay, moving on. Let me check my notes here. Let's get into some components. So we've talked about several different components up to this point. Kind of a general list. You'll have EXVs. The critical thing I want you to understand about EXVs is there's two primary styles. You'll have one that uses a common. I don't know how else to say that. So you'll have one input lead that and then you'll have gee whiz brain, come on. You'll have like four commons, or you'll have four input leads and one common lead, and basically each of these will fire. So this will be your leg 1, 2, 3, 4, and then common. And so if you're, an EXV is nothing more than a stepper motor. So Engineering Mindset has a fantastic video on stepper motors, and they took it a step further. They did one just on steppers, and then they made one on EXVs and how we use a stepper motor in an EXV to control it. So there's two primary lines of thought. Inside the EXV motor head, that's what it is. It's a motor driving a shaft on a threaded bolt. You will have multiple windings. That's what they are. They're just little bitty tiny windings that trigger, and depending on how we reverse polarity through those windings, decides how we step. So, for example, trying to think how I could even draw that winding. Sorry. This common would feed. Come on, Holden. This common would feed to a common point in the center, And then you would have 4 different internal windings, each of these feeding each one of these legs. And so to step this motor, we fire, so this would be initially positive, this would be a negative. So we'd go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Every time we go 1 to 2, that's 1 step. 2 to 3, 2 steps. 3 to 4, 4 steps. 3 steps. You get the point. And we step those down, and that's going to step that valve to a closed position till it seals off. So that's to close it. Then if we want to open it, the controller is going to flip that around, and this becomes our negative. This becomes our positive signal. And then we step that right back out. 4, 3, 2, 1, 4, 3, 2, 1. And by reversing the polarity, we reverse the direction of the current flow, which instead of spinning it clockwise, it now spins counterclockwise, the same way you would have it if you reverse 2 motor leads on a blower motor, a 3-phase blower motor. We're just changing the magnetic field, and this is all DC. Yeah, this should be all DC current. So this is one line of thought. The other common line, it's a lot simpler in my opinion. You just have 4 wires. Each of these are tied together. So you'll have a 1, 2, 3, and 4. And then inside of this, you'll have, this is by far not a nice drawing, but it gets the point across. So you'll have 2 different sets of windings doing the exact same thing. We just step, we fire this, 1, 2, 1, 2, 1, 2. And each time we cycle between the windings, in this case, 1 would be positive, 2 would be negative, 3 would be positive, 4 would be the negative in polarity. And every time we cycle that, we're taking a step. And then we just reverse polarity and cycle it right back out to drive it the opposite direction. In terms of troubleshooting these, it's pretty freaking simple. Unplug it, ohm it. But you have to know which style you have. So this one, only 1 and 2 should ohm to each other, and 3 and 4 should ohm to each other. This is common for York and, I believe, Carrier. I think Carrier uses these. Train may use them on certain applications, but Train is real common to use this style. I'm not even sure what the... No, York uses, actually they both use both. They kind of all use both. Sporlan, yeah, York and Train both use Sporlan and Danfoss depending on the series and application and revision. So there's been different revision changes. Yeah, basically, cheapest bidder. So anyway, in this particular case, you would ohm from common to each of these. And each winding should be identical resistance. And so if you had one that wasn't, obviously something's wrong. In this particular case, if you have this style, you would, if you have resistance between the windings, something's wrong. Because they should never have resistance. Something shorted internally if that happens. They do not have electrical contact. Yes, Sporlan does create a EXV tester just for this. We don't have one. Never used it. I do know it exists. So if that's something that would benefit you. One thing nice about most of our modern chiller systems is we can manually control those EXVs in a service test mode. So in our case, we can just use the unit controller as our EXV test driver. ultimately, EXVs are pretty simple devices. If you're worried about an electrical failure, if you have resistance and nothing is shorted to ground, and your winding to winding resistance is on point, it should work electrically.
But that's not to say your threads are bad or anything like that.
Right. Now, something you would see is if you were questioning if the controller was working properly, you should be able to unplug these, put your leads on the harness side from the controller on, say, 3 and 4, and your meter, once you actuate it, you should see your meter flashing. That's a good thing. That means that it's cycling the pulse. Yeah, it's pulsing that winding, and then you could check the other side. Now, most of the time that happens so fast that the meter has a hard time actually getting a real reading, so you can't verify the voltage that way. Majority of sight glasses, though, majority of EXVs have a sight glass on them once you get to this large of a scale. Now, smaller systems may not, but most of your chiller systems are going to have some kind of sight glass on the EXV. So in that sight glass is so that you can watch that plunger actuate. So utilize that to your benefit to try to verify it mechanically. Now, I can tell you, EXVs, for the most part, should be fairly quiet in their operation. If you walk up and that EXV is just excessively ticking, like you can easily hear it from anywhere, you need to start asking questions about that valve. Because it's requiring a lot of extra load on that motor of the EXV in order to move it, and it shouldn't have to do that. If you're having to do that, it's very likely that you're missing steps, which is throwing your calibration off. Because remember, neither of these have a reference indicator. There is no reference indicator going back to the control system to tell it I'm in X position. It is all done in the logic. Floating point. That's all it is. It would be nice. Don't hold your breath. Okay, let's spend a lot of time on that. Gee whiz, look at that time. Whew. Okay. I'm going to have to kind of step things up a little bit here. Control board. So something else I want to point out that's important. Transducers, I think most of us are pretty straightforward on transducer. You have input power, whether it be 24 volt, 5 volt, 12 volt. Most of them are 5 volt DC input, and you'll have a 0 to 5 output, majority of them. Not every machine has a transducer, but you may still have pressure readings on your display. So Train is probably the biggest example, and York and Carrier have done this too. There is no transducer. What they're doing is you'll have a thermistor in the two-phase line or at the bottom of the evaporator where you have or should have standing liquid, and is reading the literal saturation temperature. You know, when we take a pressure reading and we convert that into a saturation temp, that's a conversion from pressure. But what they're doing is they're taking an actual saturation at the point at the boiling point that it's happening, and then converting that actual saturation into a pressure for you. RTAAs do this. CVH series trains do this. Now, some of the newer ones have high side transducers, but even still the new ones, they're using a thermistor in the bottom of the evaporator on those centrifugals, and the low side pressure you're seeing is that thermistor reading converted via PT inside the logic of the system. So don't walk up to that trying to find where the suction transducer is. You'll never find it. It doesn't exist. Okay? Be careful. Flow sensors. One critical thing I wanted to point out with those, there's a few different styles. The most common would be the thermal dispersion, I think is the term for it. Basically, it's got a little heated diode in there. And it's calibrated to know that, you know, if that diode is generating or reading X amount of temperature, then I am or am not flowing water, essentially. A lot of times they'll have like a little flow LED indicators where it'll give you some sort of metered reading. So just bear that in mind. That's how it's doing it, is it's reading the temperature drop on the tip of that sensor, and it knows that by losing X amount of heat through that, I have Y amount of water flow. And those do have to be calibrated. They're not come out of the box, slap it in, and it's good to go. Well, I say that. Most of them have to be calibrated. Some of them, if you order them OEM, may come pre-calibrated. Like York, for example, the ones that they send you are the new series, not the old series. It's already preset. You don't even have an adjustment option. You just plug it in and go. So thank you, York, for that. The critical thing, those matter what direction they're facing. If you ever look at one of those little flow sensors, there's a divot in the head of it, where you would put your hex head, whatever, right? It's a good place for the channel locks. That's a joke, everybody. It's a joke. Please don't. Anyway, that divot should be facing into the flow of the water. So against the flow, right? So if the water's coming this way, I've got which in this case, your flow sensor should be on the leaving side of the machine, which means that basically that little dot should be facing the machine. Some of them, I think, technically have like a slight offset, so it won't be straight on. It may be, depending on the specific sensor, it may be like a eighth of a turn, just off center to the pipe. So just be mindful of that. But that is how that does matter how that goes in, because if you do that wrong, it'll still read flow, but it won't read it as accurately, and it'll have a greater potential of burning that sensor out. The other thing to note: do not put power on those sensors without water on them, because that will allow them to overheat, because they're meant to be inside of the water stream, and that can damage that sensor and to where it just ain't gonna work. So be mindful of that. If you're walking into a system where you've got to drain the evaporator or the barrels for any reason, and you still have power on the machine, meaning those sensors are still reading something, unwire those before you drain that water out. That will protect your sensors. We need to get into, I'm not going to dive into this. We need to get into loading and unloading. Any questions so far? Okay. Everything about the loading controllability for a chiller is based off of the leaving water. So entering water matters up to the point of making sure that it's not inverted. In the event that you have your, if flow was to legitimately get reversed, on a machine. You could have that, and
First day you had that on that deck.
yeah, that can happen for various reasons. Somebody made a mistake, flow's running backwards through the machine. It's going to see that as inverted temps, meaning what should be your entering water is colder than your leaving water. It's not okay with that, and it's going to give you a fault because something's not right, and the chiller is smart enough to know that.
Can you just swap your sensors and be okay? Or is there other things that I'm missing there?
No, you cannot swap your sensors. Don't do that,
I mean,
please.
for the chiller reason, but I know the lube would have a fit.
Well, yeah, the whole system doesn't work if you swap the sensors. It won't. No, that doesn't. At that point, you no longer have counterflow,
No, that's true. Yeah.
right? Just no. That just remove that thought from your brain. You're not swapping the sensors.
This is like
But most of the time when you see that, it's got nothing more to do than just a bad sensor. So either whether it be the entering water or the leaving water, one of the two have gone bad, is reading out of calibration. And so a pretty common one I've seen that alarm with is a train. Their sensors just fail, and the leaving water will go to like a default 100-something degree value. And when it does that, obviously that's warmer than your entering water, at least I hope so. So it's going to see that as an inverted system, and it's not going to let it run. And now, in a case like that, so when I run into that in the field and say I have a bad leaving water sensor, but my entering water is good, I will remove the sensor completely and unwire it, and then reinstall it on the leaving water and swap them that way. I'm going to say that very specifically so I don't get mixed up. I got to give you a hard time. Anyway, I will do it that way because at that point, the machine doesn't care that it sees 100-something degrees entering.
Right, that'll get you up and running so you can go get the part.
Yes, it is satisfied that the leaving is making set point. So just bear that in mind. It's the leaving water that is controlling everything that happens in that machine. So,
and everything's more like just for informational purposes.
Or just safety. Yeah, it's information, data, it's safety. Those are really probably the two primary things it's used for. Everything else in the logic is looking at the leaving water and to decide. So, most of the time, a chiller you'll have two different parameters. So in a normal air conditioning application, if we have a set deadband range of say 2 degrees or a half a degree, 1 degree, whatever. So if we get 1 degree below set point, we turn off. 1 degree above set point, we turn on, and we cycle between those parameters. In the chiller side, we do this a bit different. You may have a shutdown of a 2 degree deadband. So meaning if we have a 45 set point, we shut the chiller down at 43 and we stop mechanical cooling. But you may have a restart of 10 degrees. So that means that 55, you're bringing the mechanical cooling back in. 55. Because it's based off a set point, because your set point was 45. So you'll have two different parameters. Now, not all of them do it that way. Some of them, if I remember right, I think Train had it on one of their series where it was the same number. Like you had, I think, a maximum of either 2 or 4 degrees either way, which I wasn't a huge fan of. I forget which controller. I think that was on the UPC2. And it wasn't even on all the chillers. It was on specific revisions, because I could do it on some and not do it on others, or something along those lines. Anyway, let me check my mic battery. Yeah, we're still doing good. Okay. So just in terms of starting up and shutting down, just bear that in mind. As I was talking about earlier, for it to stage up the other circuit, it's looking at the RLA. So if that circuit stages up to 100% RLA and we're still not satisfying set point for, say, 5 minutes, then it's going to say, okay, I need to bring in another circuit to help me out. Train does not stage down the other circuit, or the one that's running. So let's say circuit 1 was the one online. It will leave circuit 1 fully loaded and bring circuit 2 in and start to load up circuit 2 to help. If I'm remembering correctly, I don't think it cycles 1 down until after 2 comes online or something like that. York, on the other hand, does exactly that. If it goes to bring in a second circuit, especially because of the VSD, it ramps that circuit, whatever circuits are running, even if you've got a 3-circuit machine, it's going to ramp those other circuits down to minimum, bring that extra circuit in, and then all the circuits will ramp back up together. And as I'm sitting here talking about it, I think I'm saying that wrong about train on the screws specifically. I think train screws, it will ramp those down, bring in the other circuit, and then allow both circuits to ramp up together based off of current limit.
Do they call it like load shedding or something like that?
No.
I know yours do that.
No, it's just staging the machine up. I don't think that's referred to as load shedding. I don't know. Anyway, so we do that to give us more capacity so that we can catch up. And you want the circuits to be able to stage together, because part of what they'll do on the inverse side of that is say, okay, we had to bring in a second circuit to keep up. Load on the building begins to reduce, the circuits begin to ramp down, and eventually they're going to get down to their minimums. So they're both circuits are running fully unloaded, and we're still overcooling. So if our differential for shutdown or stop was 2 degrees, once we hit that 2-degree mark and we hold that mark for more than so many minutes or seconds, then it's going to drop out that lag circuit. So in this case, we'll say circuit 2. Circuit 2 is going to shut down, and then it's going to start to ramp circuit 1 back up to catch the load. Because the 2 of them together, they both running at minimum was too much, but we shut this one down. Now we can run where both of these couldn't unload past 30% each, but we needed just one of them to run at 40% to maintain load. Well, with both of them together, we've technically got 60% of what we could have. So we shut this one down, and we bring this one back up 10% of its load, and now we've perfectly matched our target set point, or leaving water set point. And it's just going to sit there and cruise at 40% instead of the 30.
That's exactly what boilers do.
Right. I mean, it's all the same basic theory. And The only difference between this and a scroll, scrolls use the same logic. Our ability to match load is significantly better. So a scroll, we have, stages of 30, 40 tons at a time. And that's all we can do. We can just bring in 30 tons or drop 30 tons. A screw can dial that in much more refined to where it can dead on match that load and just sit there. Whereas a scroll setup that second compressor may be staging off and on every 30 minutes to an hour, just all day, because it doesn't have that in-between state.
What about centrifugals? They can pretty much match like screws.
Yes, centrifugals can match. They have IGVs, inlet guide vanes, or for York, PRV, pre-rotation, whatever. Yes. So they do the same principle with an IGV. And Yorks or centrifugals will take it a step further, and they'll begin to match IGV to compressor speed. And then they'll begin to do load balancing based off of speed and IGV position to minimize the actual RLA on the machine at the same time. We'll get into that next month.
Like a fully synchronous motor.
Right. Yeah, we'll get into that next month. Now, yes, scrolls that are on drives, obviously they have the ability to better tune that. And that is technology that we're seeing more and more of. So what I'm specifically speaking towards is machines that don't have that capacity. But even in a machine that has a variable speed scroll, that's usually the lead or the first two compressors. And so you could have a 4-bank circuit, and 1 and 2 may need to fully stage, but by themselves, they still need that third one, that in-between point. Now, I know some of the logics can get kind of crazy to where it'll stage 3 on, shut 2 down, and it can then ramp 1 to match, or ramp 2 to leave 1 100%, 3 on, and then 2 can then match load, and like they can do that kind of stuff. Yeah, Aeons that's exactly what they do.
Aeons basically they'll have the 4 2 will be variable speed 2 or just
Yep.
off on.
Yep. So it's that does exist. So yeah, I mean, I'm not to neglect that. So screws, like I said, they can precisely tune that in and match that. And the best thing a chiller can do is never turn off. And an even better thing it can do is never need to cycle compressors ever. Meaning, in a screw scenario, second stage. Or even in an RTAA situation. So RTAAs, you get above, 250 or 300 tons? You have 2 circuits but 3 compressors. So circuit 1 has compressor A and B. And then compressor C is circuit 2 by itself. And then you could have, I think once they get up to 350 or 400 tons, circuit 2 has 2 compressors and circuit 1 has 2 compressors. So in that particular case, you would only be running, so say circuit 1, you would only run 1 of the 2 compressors on that circuit. And in a perfect world, you never need to cycle that other compressor. But in reality, to match the load, sometimes that will need to happen. So that's when a screw becomes very inefficient. So one of the benefits that I like about scrolls is most of the time scrolls have the ability to match lower load conditions better with lower amperage. In a scroll, when you have a system that has fairly low normal operating parameters, but can sometimes see excessive highs, that's where a scroll really shines in its ability to capture its efficiency, because it can unload with a lower amperage more than a screw can. But where screws really shine is when you have a elevated sustained load that is consistent. You cannot defeat, or a scroll can't compete with a screw in its ability to match the load and generate efficiency at that point. And that's where they really have their best market. So, now most machines, as we stage compressors up and down, we have to also maintain our head pressure and superheat. So most of your air coils are going to run anywhere from about 4 degrees on the low end, usually, to up to 12 degrees of superheat is pretty standard. Yeah, with an EXV. Yeah, if it was TXV, I would not want to run below the 8. Yeah, so if you're dealing with a TXV situation, don't drive that thing less than 8. Those TXVs do not have the precision to safely protect that compressor. But with an EXV, you can safely run at that without having to worry about the compressor, because it can respond fast enough when it needs to. I think for sure Train, a lot of the smaller RTAAs, like the 70 to 120s, I think, or 130s, they will run like a 4 degree superheat. But some of the bigger ones usually are more of that 10 degree mark. RTACs. So RTACs are not actually controlling off of superheat, but they do run. I'm trying to remember. I don't even know if they give you a superheat value. Like, they don't on the controls. RTACs, to my memory, do not read superheat at all. I don't even think they have a suction thermistor. I could be wrong on that, but I don't believe they do. They're controlling based off a liquid level. So RTACs have a liquid level controller or sensor that it's going to open and close the valve in order to maintain a set level of liquid in the evaporator, and it knows that by maintaining that level of liquid, we should be achieving X amount of superheat on the machine. It's a calculated value. We do the same thing with York centrifugals. Just we're looking at condenser level, condenser liquid level to control the metering valve on like a York machine, whereas that RTAC is looking at evaporator liquid level. So as long as the liquid level doesn't exceed set values, you're not going to have a superheat issue. Particulars in what way?
What are the differences over, like, what would be normal, conventional, like scroll?
As in superheat?
I'm just asking about like operation period, because those are becoming more and more and more popular.
Well, we'll get into the centrifugals and turbo cores and all that next month. We could spend another 5 hours just on that. Yeah. Let's see. Yeah, it would be evaporator superheat most of the time. Now, like Train is reading. Honestly, most of them you would consider that more of a. We're talking suction superheat, so evaporator superheat. If you're talking compressor superheat, I would assume you're meaning discharge superheat, which is on the high side of the system, and those are totally different parameters. So a lot of the times your discharge superheats will float, let's see, so I think York tries to maintain less than 40. And I think if you exceed, was it 45 or 50? I'd have to look back in my books. It's going to trip on a high discharge superheat fault. Whereas I think trains run a little bit higher. I think they'll push 50 or 60 somewhere in there before they start having faults and issues. And then centrifugals run way less than that. Keep in mind, the reason the superheat comes up as a topic, we have to be able to maintain EXV position as we stage up or stage down. So that's part of your evaluation metrics you have to pay attention to, is the more you load, that EXV has to be able to keep up, and so does that refrigerant stream. So that is just as much a part of the loading and unloading sequence. And what that will lead to is you can have a suction limit pop up, even during pull downs. So if you're in a startup state and going into a pull down, and even before you get to your pull down RLA limit, or current limit, you might see a suction limit pop up on your display. And that's because usually that's around 30 to 32 degrees of saturation, somewhere in there. It'll go into a suction limit, and that's because your EXV has to be able to catch up. So one of the things that can happen is, the machine turns on, is starting to ramp up, you see it goes into a pull down. I've got a pull down current limit of 80%, but for some reason it stopped at 60% and it won't go past that. Well, if you start looking into your parameters, you'll see that it's telling you it instead of a current limit, it instead is limiting on a suction limit. And that's because, the EXV has not been able to maintain feeding enough refrigerant to the evaporator to keep you from pulling into a low pressure state. So it's trying to stop you from having a nuisance trip. And that same thing can happen on just a regular loading. And so if your compressor is loading up and you see it stalls out at 85% current limit or currents, even though you've got a 100% limit, that is because if you go in and look at your suction side, you may see that you have maybe a low flow, or maybe you've got a low charge issue, or maybe that EXV is out of calibration. It thinks it's opened all the way when it's really not. And so the EXV needs to be calibrated, but because of that, it's not flowing enough refrigerant. So it's going to stop that compressor so that it can process as many BTUs as the system will allow it without going into a safety trip. And the same thing can happen, not all machines do it, but some of them have head pressure limits, if I remember correctly, to where if it starts to push the upper limits of your head pressure before it gets to a high pressure trip, it will try to limit the loading on that compressor to prevent the high pressure. I don't see too many of those. Most of the time it's the low side that's possibly. Well, but you can still, so that goes back to loading, right? If you're in a pull down and your coils or whatever, your fans, or say your coils are dirty, or you got a bad fan or something along those lines, and the condensers are having trouble keeping up, you may have enough current limits to push the condensers into a trip state. So if you tried to run 80% current limit with a 70-degree entering water, that could be enough to trip you on high head pressure at 80%. So by the time you hit 75% and you're at that upper head pressure limit, the control system, so that at least it can run, and it's not going to push itself into a fault on purpose, because it's bad for everybody, and it knows that. So it's going to stop short of your current limit because the head pressure limit caught it first. Just like on the low side, that low pressure limit may catch it before the current limit does. So you've got multiple safeties that are working simultaneously to try to keep this machine online as smooth and long as possible. Um, 728. Man. Yeah. So something we're talking about, and I'm thinking it's probably going to be a pretty good idea. We'll keep the water-cooled overviews for next month as planned. But I'm thinking maybe the month after that and for a couple of months, and we'll have to talk it out on the automation side too. Taking some time to go more into the specific parameters of each individual machine. And so we may have a class where we spend the class talking about the specifics on RTAA series and maybe an RTAC. And then the next class could be over YVAA versus YCIV or CVH series. Here's all your data limits. Here's how everything should work on this specific machine. And maybe we go through something like that. I don't know. We got to talk that out, decide what we want to do. So, because the fact is, we want to get this chiller training in for everybody. But if we were to do this genuinely, we could spend the next year going over all the various nuances.
Factory training is a few days at 8 hours each. So.
Right. Yeah, we could spend months going over all this stuff, quite literally. I'm barely scratching the surface in these 2 days. Barely scratching the surface. I'm just trying to give you a basic idea so that when you walk up to it, you don't have to drool on yourself. That's really what my ultimate goal is here. So, yeah. That's basically.
This is a call for you. I got a parking lot this week.
Yeah. So anyway, we'll talk that out. We'll get the training committee together, and we'll figure that out. Either way, any final questions before we check out? If I don't stop now, we're not going to stop for about another 30 minutes to an hour. So, we're good? Okay. Appreciate it, everybody.